Okay, so welcome everybody to the Empower the Innovator Summit. Sorry, I cannot be there in person. I had another speaking engagement at this slightly before right now. But we wanted to do a session on what we've been doing in the world of electric vehicles and electric power measurement. So thank you for joining my session, and thank you to Aikawa-san for translating to Japanese. And this session is power measurement techniques for real-world drive cycles, including power hardware in the loop. I'm Mitch Marks, head of business development for Asia, and specialist in electric motor testing. So thank you again. Just as a review, since I don't think all of you are super familiar with our electric vehicle testing solutions, we have a modular platform we call eDrive for measuring high voltages and currents, accurately measuring electric power, and all of the mechanical signals that might go along with it. We do a simple data collection of electric and mechanical signals, so we make it really easy to see from battery to wheels or propeller. We make very fast and accurate efficiency measurements. We can help accelerate your testing. We'll talk about that a little bit. We can expand out to many channels or a wide variety of channels, so we like to say we're future-proof. Uniquely amongst competitors, we record data and we offer a scope functionality, so you can really see what's happening in your test, and you can combine multiple instruments into one package. So you can start to save some money and simplify your testing requirements. Lastly, we do all of our calculations in real-time hardware. This allows us to move more quickly, reduce data post-processing, and to offer really tight integration into a test cell or hardware in the loop, which we'll also talk about in this session. We offer sensors, torque sensors, current sensors, force, accelerometers, data acquisition, and power analysis, and then some software that's really powerful for understanding the full spectrum. And then, especially here in Japan, we have an excellent support team, and this presentation will feature products by HBK. So for those of you who are familiar with this, what have we been working on? We have a really nice solution for dynamic power and drive cycles. That's what we're going to talk about today is some of this dynamic power and what the future is and what we're seeing global customers do. And it's really looking at the real world applications of these vehicles. We're looking at electric motor sound and vibration. I understand there's quite a few people here with a noise and vibration background. Please bug one of our people and speak to them about torque ripple or electric motor noise and vibration, because we can offer the electric measurements as well, which I think is really compelling for doing your analyses. Advanced motor calculations, we get into the real motor nerd stuff. And then we have also been working on electric aircraft. I think many of you might have some secret divisions where you are working on some electric vertical takeoff landing. And that's featured here on the right. We have some cool new products. Again, please ask one of us about that. And I skipped my animation here, but we can have lots of distributed chassis with high voltage measurements spread a wide distance. Exciting stuff. We've had a lot of development going on. But let's get into the meat of the presentation. So as many of you may know, this electric powertrain has kind of three main components. We have the inverter, which supplies a high frequency voltage. This is in the 10 to 20 kilohertz. This feeds the electric motor, which acts as a filter to filter that high frequency voltage down to a current with a fundamental. So we have this high frequency, 10 to 20 kilohertz. We have this fundamental frequency that's driving speed. This is maybe 0 to 1 kilohertz. And then this results in a torque and eventual output at rotational frequency. So we have torque that has some torsional vibration, and many of these things get out to radial forces and sound and vibration. And what I want the important takeaway to be here is that this is a very dynamic system. It has 3 frequencies: switching, fundamental, and rotational. And that inverter is a computer that we can tune to affect all of these outputs. So we have this electric and mechanical system that's very dependent, but we can also change on a dime how that inverter operates. Now, in that electric powertrain, we have losses, and we all want to measure these losses and characterize them. So we have our battery, our inverter, our motor, and our gearbox. And we have DC input, mechanical output. We have inverter losses, motor losses, and mechanical losses. And a lot of the job of the motor engineer or the control engineer is understanding where these losses go so we can minimize them. But what affects these losses? Once the machine is born, the inverter is born, what affects these losses? Well, there's kind of three main factors, and we could argue that there's more, but let's look at battery voltage. The motor and inverter respond differently as that battery decreases. And as that state of charge goes down, that battery level goes down. Temperature. As our temperature increases, our loss is going to increase because that copper gets hot, the resistance increases. So we need to account for battery voltage, we need to account for temperature, and we also need to account for the environmental part, the noise and vibration. The experience of the vehicle matters, and there's probably more factors than the sound and vibration. But if we have an extremely efficient point, but it's bad for durability, it's bad for sound and vibration, we may not want to operate there. So we need to account for these conditions. What does that end up looking like? And this is probably a review for many of you, but we end up with this efficiency map is how we traditionally, keyword traditionally, have characterized this. We set a torque, we set a speed, we measure a point. We change torque or we change speed, we measure a point. And eventually we get this contour map of what the motor efficiency looks like across its speed and torque operation. And this motor map, or this efficiency map, is like a fingerprint of what the motor does in different scenarios. So we want to execute an efficiency map for each state of charge or battery voltage, for each temperature, because this vehicle is going to operate from quite cold to quite hot. And then the different control types or the different experiences that we might want to execute with our inverter. These tests become quite time consuming because they must be taken at a stable torque, a stable temperature, and a stable speed, which means we need to wait and then measure, and wait and then measure. And eventually we'll produce this nice color map. And this is how we've done motor testing for many years. And we get an output that looks something like this. We fix a speed, we go through a range of torques, we record our voltages and currents, and we move to the next speed, we move to the next torque. And here's a zoomed in area of data from maybe a dozen measurement points. We have our torque, our speed fixed, we measure our voltage or current, and eventually we produce a map output. And for those of you familiar with the HBK eDrive system, we do this automatically. This is what we're really good at. We allow you to make a measurement very quickly, move to the next point, make a measurement very quickly, move to the next point, and plot a nice efficiency map live. Many of you might be familiar with this, but it could be new to some, so we'll review. So what we find is that these efficiency maps are quite time consuming. And this is a case study we did with a partner company to really compare us with a competitor. And we took a very low density efficiency map, 200 points per map, which we're seeing a lot of the auto manufacturers do 1,000 to 4,000 points per map. So this is very low density. We took 5 temperatures and 5 states of charge, which resulted in 200 points per map times 5 temperatures times 5 battery voltage equals 5,000 measurement points. We had the testing and transitions, we had heating up and cooling down. We actually did not account for the other transient calibration retesting. And what we find is that for this 200 points per map, or 25 maps, 10 seconds per measurement point took about 70.5 hours. With 1 second per point. With our eDrive system, it's about 13 hours. And I apologize for this being in US dollars, but that equates to about 17,000 US dollars if you were testing at an external test house. And what we find is that the longest delays are really in that heating up and cooling down, keeping in that temperature range. So by testing more quickly, you can actually test more quickly because you're not spending as much time heating up and cooling down, because you spend less time at each operating point. But this is really to demonstrate that this is quite a time-consuming test. HVK is very good at helping you accelerate this. How do we do that? So we do that acceleration with a technology we call cycle detect. So in our cycle detect, in our measurement system, we have a real-time digital signal processor where we do all of our calculations in hard real time. And in that digital signal processor, we have a function where we track the fundamental frequency. The fundamental frequency in the current is proportionate to speed. We identify zero crossings. We take 2 consecutive zero crossings, and we have this square wave that indicates our averaging period. For those of you who are not familiar with electric power, you need to do your calculations on a even number of half cycles to get an accurate measurement. It comes down to the symmetry. So we take all of our points, we calculate our RMS, our power, our efficiency. This one prevents us from needing a settling time. We don't have to wait for an instrument to lock onto a frequency, constantly tracking the frequency. So we can move very quickly. Rather than 10 seconds, we can test in 1 second, half a second, 1/10 of a second, or faster. We can also average as many together as you want, so you can account for maybe an instability in your control. But this allows us to test very quickly. As we'll see in a moment, it allows for some other things as well. But this cycle detect is key to what we're very good at, which is testing fast. And as an example of how that helps us test fast, if we look at a traditional fixed time method, let's say we need to measure for 1 second per measurement point. Well, at low speed, our 1 second gets us a couple of rotations. As we increase speed, we get a couple more rotations, but we're always measuring for that fixed time period. This is just measurement. This is not transitions. Now, if we do a cycle basis, let's say we measure 1 cycle. Well, at low speeds, this might take a little longer. But as we increase speed, we can actually test more quickly. At high speeds, we can significantly reduce our test time. And rather than a fixed 1 second, or realistically with some competitors, 10 seconds, now taking a fraction of a second, we can significantly reduce that test time because we only need 1 or however many cycles you choose. So we can reduce the test time by using this cycle basis. We can really test as fast as your dynamometer can go. Now, if we extend this cycle basis to its natural conclusion, we get something very interesting. So here's where we're going to start talking about dynamic power. I don't think any of you would be very surprised that vehicles are constantly changing speed. Here's an example we took from some track data on an electric vehicle, looking at torque versus speed for electric vehicle. And these 3 different field runs, we find we have a lot of operation in some very similar areas. So when we're tuning the vehicle, we don't necessarily need to focus on the whole operation spectrum, the whole torque speed curve. The vehicle spends most of its time in small pockets. So if we optimize over these small pockets, we can effectively increase the range of the vehicle. So from a development standpoint, why would we focus on that full map when we could focus on these high use areas? This is where the real world vehicle duty cycle and the cycle detection come together. So what we find is that these motors don't behave nicely in the application. As we're speeding up, as we're slowing down, as we're changing torques, the motors require extra energy to perform these tasks. So in a steady state, they're going to require less energy than when they're changing speed. These controllers, the motor controllers, also have overshoots and resonances. So as we're changing speed, it might overshoot, undershoot, and have an oscillation. This also is going to consume more energy than a fixed speed. So why would we want to characterize all these fixed speeds when we could look at the actual in situation? There's plenty of reasons why, but I think what I'm going to argue is that we should also look at optimizing energy consumption over the real vehicle duty cycle. And the cycle detect enables us to do an accurate measurement during changing frequencies. We do not require a fixed speed. So as you're changing speed, we can give you a very accurate measurement. And what we have on the right-hand side is an example of a vehicle starting up from zero speed. This is actually a scooter, so you have to have a little back EMF as it's rolling. The inverter kicks on, we have power flow, and we can see our cycle detect, this black square wave, tracking that current. And we're getting a very accurate power measurement as the vehicle is changing speed. We can see how it handles regeneration. We can see how the controller responds. We can identify overshoots and controller issues so that we can start to optimize the vehicle efficiency in the real world. And this is what cycle detect allows us to do. It allows us to measure power, measure energy, and optimize the real world situation. So what does this end up looking like in practice? This is what we refer to as drive cycle testing. Another thing I don't think will be any surprise to you all, especially from the automotive side, is that we have these standardized drive cycles. I have 5 of them on the screen. Some of you may be familiar with WLTP, WLTC, here's NYC, LA92 is quite popular. These are different standardized speeds versus time that we can use to compare vehicles. And this similar things are used for the certification of the vehicle. We're getting that highway range, we're getting that city range, we're getting the total range of the vehicle. And we'll characterize the vehicle and use a chassis dynamometer to simulate the torque. And often the certification will be done with this. But these have no steady state. They're constantly changing speed. So why don't we characterize and understand the vehicle as we're changing these speeds? We can optimize our control. We can increase that range by using these types of measurements. And now HBK is incredibly good at this, and we'll look at this in a moment. This is where things get exciting. So we can analyze the total energy consumption and the dynamic power very well. We can record that data. Here's the DC for voltage, for current. We have the power, and we can see these dynamics in the power. We can understand that this overshoot, this resonance, are areas we might need to adjust our control for. We can very accurately look at that energy consumption throughout. This becomes very realistic to also do on a dynamometer. And this is an example of a test that was done with HBK equipment, looking at drive cycles. And some of you in the audience might find this motor familiar. It is a university-funded project from a Japanese auto supplier. So we have our speed on the X in blue, and we have our torque in red for 30-minute drive cycle, and this is the WLTC. And throughout that, for 7 different motor controls, so each color indicates a different motor control, and the red one is the optimized. We were able to identify where do we have the most power losses for a given operation? Where do we have the least power losses? How do we make those transitions between motor controls to increase our range? And what we can see is that red optimized has very much eliminated some of these big spikes. It's minimized the temperature rise throughout the operation. In the middle graph, we have temperature. And it's also reduced the magnet temperature. So by reducing the losses, we've reduced the thermal loading, and we've reduced the risk of demagnetization. This is done by optimizing over a real-world drive cycle, by measuring the dynamic torque and speed, and the cycle detect is what enables that. Very powerful what we do, allows for some very cool testing. This is done on a dynamometer with the eDrive system. We can characterize those power losses cycle by cycle so you can optimize the range of your vehicle. And now here's an example of some dynamic power, and this is the difference between HBK and competitors. So we record the data, so I was able to do a really nice comparison. Where we have, again, our voltage, our current, and I have power dynamic and power slow average. Many competitors are going to give a wrong answer because they don't have a settling time, but here even just their calculation method, which is maybe 5 or 10 hertz, versus us, which is in the 2 kilohertz range. We can see our power. We can see these resonances with the high frequency. We can see overshoots with the high frequency. If we go to the more slow calculation methods, we miss resonance. We miss energy loss. We miss an overshoot. We have a 2 kilowatt difference between the measurement. We miss an overshoot by 2 kilowatts. Here's an area we could tune. We could save energy loss. So this is the real benefit of having a dynamic calculation, is you know what happens, so you can tune your controller. Looking at the AC, so that was just the DC, but it makes for a very easy, clean example. This is the AC example. This is using the cycle detect. This is a vehicle coming to a stop. We can see our frequency is decreasing. We can just see that getting wider and wider. And here we go into regeneration. So our power comes down to 0, and then we go into regeneration. And we can understand how our vehicle handles regeneration. And what I find very interesting is over here, where this increases, and now instead of regenerating, we're wasting energy to stop the vehicle. This is something we could look at with control. And the cycle detect allows us to accurately trust all of these measurements and characterize this vehicle in its real-world application. We can increase this regeneration. We can increase our range. So again, we're not necessarily replacing all the efficiency mapping. We're introducing a powerful tool to understand how our vehicle handles these different control techniques. We can see the details. We can see that wide bandwidth power. So we can reduce energy consumption. We can reduce thermal loading. Now, how do we take this even further? This is what customers are doing today. We're seeing this in China, a little bit in Japan, India, United States. It's becoming more popular. I hope some of you adapt it. What's next? Where's the real innovation? This is the Empower the Innovators Summit. Power hardware in the loop is what we see coming next. Now, for those of you who don't know, power hardware in the loop is one or more real components combined with a model, a computer simulation, and a power amplifier. So we have a simulation running on a real-time computer, like our concurrent real-time platform, telling a power amplifier what to do. This power amplifier is interacting with a real component, whether it's a motor, an inverter, a solar panel, and we are acquiring the data and feeding back those real-time equations. Because we do our calculations in discrete time, we can feed everything back. We get that accuracy, we get that data recording, and we can offer that real-time feedback. So where does HBK eDrive fit with this? So we have our real-time computer. We're making the physical measurements on whatever is real. We're doing the calculations. We're offloading. These inverters are at kilohertz. We're taking that kilohertz information or megahertz data on kilohertz events. We're reducing that to 1 to 2 kilohertz calculations and feeding that back. This reduces the PC loading on the real-time computer, gives it a very high bandwidth feedback, and allows it to make decisions quickly. We can do this because we have roughly a 1 millisecond latency. and we can offer up to 2 kilohertz feedback. We can then record all the data, that really high accuracy data. We can compare it to your test data. When we do the calculations, we offer the feedback, we unload burdensome calculations off of that real-time computer. The goal is to take something like a real test where all the components are real and move it to a situation where maybe just my inverter is real. I simulate my motor, I simulate my battery, and I still make the same high quality measurements on my power hardware in the loop that I do with my real measurement. I can tune my models. I can increase my model fidelity because I understand the difference. And I can accelerate my testing. I can test hard to test areas. Fault conditions are very difficult to test. There's some dangerous areas to test. We can really accelerate the testing with powered hardware in the loop, still have the high data fidelity, still have the high data quality. If we look at an example, this was done with a university in Canada, where we have a real-time computer, some power amplifiers, we have our measurement system, we have the eDrive, and we have the simulation PC. And it's a little bit of an ugly setup, but university. But I want to hit some key points. The reason that they like doing the hardware in the loop simulation with us is that we recorded their inverter, their power amplifiers, at mega samples per second. But we did those cycle-based calculations to reduce that mega samples per second down to kilosamples per second, which we fed back to their real-time computer. Same with the voltages. Rather than feeding back this high frequency PWM, we fed back a very stable, dynamic RMS calculation. Low latency, up to 2 kilohertz feedback, really significantly reducing that CPU loading. We can help increase the throughput of that test. And in that comparison at the university, we compared a real test stand with the power hardware in the loop. And here's data recorded with our eDrive. They get the really high fidelity data for both. We can see our startup, our load steps. We can see the torque in pink. And we have some real things happening here that we don't have in the simulation. This is not a comparison of the simulation quality. It's a comparison of the data taken, so we can identify differences between real and simulated. And the eDrive lets us record that data, view it. Most of these real-time computers are not data viewing systems. They're real-time hardware. They're real-time simulations. We can take that high fidelity data. So I'll close with our eDrive system allows you to test very quickly with electric and mechanical signals. We can record all of the data for hardware in the loop or drive cycles. And because of that real-time calculation, we can reduce your post-processing, we can enable hardware in the loop, and we can enable you to accelerate your tests. So I'd like to thank you for your time. Thank you, Akawa-san, for presenting in Japanese, and I look forward to speaking with some of you. Thank you so much.